for organizing this fantastic workshop. So I'm the last speaker. It's like yeah. Okay. So this is yeah. So maybe let me start by sort of presenting the kind of the general framework. So some of you have seen the first two slides of my talk last week, but I promise that the rest of the talk is different. So the general sort of area that I'm interested in is systems of interacting particles, and let's start with this. So we have a confining potential V, we have an interaction potential W. For the purposes of this talk, I will assume that both V and W are sufficiently nice so that I have a well-defined Binfield limit, and for at least the analytical results that I will present, I will also need to assume that I have uniqueness of stationary states. I will also tell you a bit what happens when I don't, for the Binfield limit. And I start with chaotic initial conditions for simplicity. Okay, so initially the particles are uncorrelated formally, and we saw this in the last talk using different notation. We can pass to the Binfield limit, and then you can make this rigorous in lots of different ways. So we have the McKinnon-Glass of PD, so which is written there. It's a nonlinear and non-local Fokker-Planck type equation, and then we have the corresponding Binfield SD, which is written here. So again, I have the standard term here. I have the convolution of W with the law of the process. So this makes it nonlinear in the sense of McKean. The parenthesis here, parenthesis is missing. And what I'm interested in is in learning parameters in V and W from data. Okay, so I will assume that there are parameters that are unknown. I mean, depending on how much time I have towards the end of my talk, I will also tell you a bit about what happens if you want to learn the entire function W. Okay, so this is part of a kind of general kind of a broader program where we want to learn about, well, to understand the joint limit as the number of particles goes to infinity and time goes to infinity. We want to characterize the stationary states of the Binfield dynamics. In the previous talk, we saw this integral equation that characterizes the stationary states of the Binfield dynamics, and this integral equation might have more than one solutions. We want to look at fluctuations around the Binfield limit. And again, this is very strongly related to the previous talk. We want to understand the connection between uniform propagation of chaos fluctuations and uniqueness of stationary states for the Binfield dynamics. Now, what I will talk about today is inference, or learning, I guess is the fashionable word. And then there is a sort of, the next step is to do optimal control. So once you have identified several different states of the dynamics on the fly, so using data, then you want to steer the dynamics towards a desired quasi-stationary or stationary state. Okay, there is a sort of list of recent papers. So what I will talk about today is mostly two papers with Andrea Zanoni, who was a student at EPFL, first a student of our good friend us here, and then he was with me. So it's this eigenfunction martingale estimators for interacting particle systems and a method of moments estimators. I will focus on these two papers. Now, again, no, you can also do things in a more kind of data-driven way. So there is this work with a bunch of Greek people from Johns Hopkins, machine learning for the identification of phase transitions in interacting gates and phase models. So an interesting question in this whole business is to learn phase transitions from data. I will talk a bit on this. And Thomas presented this work on Wednesday, I guess. Now, again, so yeah, in the previous talk, we heard about sort of this nice approach to proving exponentially fast convergence for the Binfield dynamics in relative entropy. One can sort of study the connection between the presence or absence of a logarithmic Sobolev inequality in the Binfield limit and the uniqueness or not of stationary states for the Binfield dynamics, and this is done here. Okay, now we can first sort of think of the inference problem in a somewhat more general setting. So I have this drift term B, and it's a nonlinear, like a McKinnon SD, so it depends on the law of the process via mu t theta. theta represents the parameters that I want to learn from data. And even though I'm interested in the grading case, because I'm interested in connections to problems in statistical mechanics and so on, so I want to have Gibbs measures and so on. So now the crucial, to my mind, thing that one is to clarify is what is it that we're assuming that we're actually observing, okay? Or if you like, what is the measurement model? We can think of paths generated from the underlying interacting particle system. So IPS, that's our interacting particle system. And this means that we are observing particles. And this is what I like, okay? So in fact, I will kind of insist that this is my measurement model. In the mathematical statistics literature, quite often it is assumed that we can observe independent paths of the McKinney, but I don't like this because to my mind it's quite artificial. Of course, if you do this, then some of the proofs become much easier, and then you can also do non-parametric stuff and so on. And then you can assume that you're observing a single path from the McKinney as well as the law of the process. But again, this is cheating, right? Because this goes back to the case, well, the non-Wheatfield case. So I will kind of insist on the first measurement model, okay, that I'm observing particles, trajectories of particles, okay? Okay, so now, right, so maybe I should give you a list of the things that we have done, and then I will skip lots of the stuff that I have prepared. So the first thing, of course, you want to do is maximum likelihood, right? So you assume that you're observing particles, and then you want to infer parameters in the mean-field SDE by doing standard maximum likelihood estimation. So the only technical difficulty here is that your model is not really compatible with the data unless you send the number of particles to infinity. But again, sort of this has been studied quite extensively. So there's an earlier paper by Kasonga from 1990 that is very nice, a paper by Biswell. And then there is a very nice and quite complete analysis of this problem by Meitner and Hoffman. So it's called the LAN property, local asymptotic normality property for the likelihood function. Now, in this paper with Louis Sarek, who was a PhD student at Imperial, who sort of was the driving force behind its project, and Nicolas Candace and Panos Parpas. There is a very long archive version of this paper where we do also the maximum likelihood, but then we removed it from the published version. Well, figured out that other people had already done. But anyway, so you can do maximum likelihood. Again, the only sort of complication to what we learn in sort of of course, like inference for diffusion processes, is that the data in the model become compatible only in the limit as n goes to infinity. But this is not a major difficulty. You can prove that, so the maximum likelihood estimator in the limit as n goes to infinity converges to the true values of the parameters, and you can also prove a central limit theorem. Okay. And this is the Fisher information matrix. Now, in the results that I will present today, so basically, I'm working under the assumption that I have a nice unique invariant measure for the mean field dynamics. So if you like that in this setting where I have a confining N10 interaction potential, that V is strictly convex, and W, the interaction potential is merely convex. This is enough so that I can prove all these results. And most of the proofs follow very closely the propagation of chaos proofs. In fact, I find this quite interesting that somehow you get the right kind of statistical methodologies by following quite closely the kind of analysis that needs to be done. The difficulty and the sort of crucial point is proving the invertibility of the Fisher information matrix. Okay? This is most of the work that needs to be done. And there actually you do need to make additional assumptions because there are issues with non-identifiability for the mean field dynamics. Okay, it's quite easy to cook up examples or to find examples in practice where it's not true that you can actually identify all parameters in the mean field model. Okay, so one has to be quite careful. But anyway, so this is what we get from maximum likelihood. And then, so the kind of my running examples here will be, so again, I have this confining interaction potential, and I will take V of x to be x to the fourth, well, I guess a x to the fourth over 4 minus b x squared over 2. I will take w of x to be the quadratic, or if you like, your revised interaction. And I want to learn A, B, K, and the strength of the noise from data. Now, for this model, we do have no uniqueness of stationary states. That's sufficiently low temperatures. So the experiments that I'm showing you here are at sufficiently high temperature so that I have a unique stationary state. And of course, we can confirm that the results that we get agree with the theoretical results. So the convergence has the right 1 over, well, square root scaling both with respect to n and with respect to t, as it should. Now, the next thing we did was to do online parameter estimation, and this means that we do stochastic gradient descent in continuous time. There is this very nice series of paper by Siriano and Pavliotis where they use stochastic gradient descent in continuous time as a learning algorithm. Okay, as an algorithm. We followed quite closely their approach. Again, now the point is that we want to learn parameters in the mean field model using data coming from the particle system. And in fact, so you can also do this if you have multiplicative noise, and you can make some link with a Levi-area correction and all this stuff. We did this with Sebastian Reich and Andrea Zanoni recently for the finite dimensional problem. But anyway, so this is the dynamic that I will run for the parameters. Gamma t is the learning rate. And I want to show that, again, under the assumption basically that you have uniform propagation of chaos, right? So this is the assumption that I make on the dynamics, that this converges to the true values. Again, I don't want to get into the technical details, but if we assume that we have continuous observations of particles, then we can prove convergence of stochastic gradient descent in continuous time. And all the stuff, of course, is quite technical on one hand. On the other hand, as I mentioned, it really follows the kind of standard scheme. So if you have uniform propagation of chaos, then the Poisson equation that you can associate to the generator of the n-particle system has nice properties. Okay, and how many follow from this? Okay, so some numerical experiments here. So this is this Hexel-Krause model for opinion dynamics. So I have a kernel. So the interaction kernel here is either a characteristic function, or I can approximate it by, well, multiplied by a Gaussian. So I have parameters there that if you think of the Gaussian as the variance of the Gaussian and the strength. So again, those of you who are familiar with this model, there is this influence radius parameter, right, that controls. So this basic model says that we interact with agents in opinion space that are close to us in some appropriate metric in opinion space. So there is no structure in space. And then depending on this radius, this influence radius, as well as the strength of the noise, you might or might not have consensus formation. Anyway, stochastic gradient descent works very well for this problem, and we can learn the parameters in the model. We tried very hard to find kind of real data to use, also with Ben Goddard here, in fact. But it turns out, I mean, this kind of Hexel-Krause models are very nice, but it's not clear what is it that they actually model. So I mean, there is data from referenda, right? So if you have this kind of binary choice, it's a bit easier and so on. But anyway, here we're still using synthetic data. And yeah, okay, yeah. So you can see now you can take also this, like your kernel, if you like, in this mean field model or the system with interacting agents. You can allow for they call this heterophilous dynamics. So you might also be talking to people who are away from you in opinion space. And yeah, you can learn the parameters as well, using stochastic gradient descent in continuous time. So this is a very nice method. So highly. Okay, now the next thing I want to move on, and this is done work with Andrea Zanoni, is this martingale eigenfunction estimator. So the way this works is as follows. So we first learn the eigenfunctions and eigenvalues of the generator of the process. And from this, we can infer the drift and diffusion coefficients. So maybe I should first present this. Yeah, let me start with this. So we solve, if you like, the eigenvalue problem. So lambda z's are the eigenvalues of the Fokker-Planck operator. The phi z's are the eigenfunctions of the operator. If we can learn them from data, then we plug this into this so-called score function, and the roots of the score function provide us with unbiased estimators for the parameters that we want to learn. This is a kind of very nice theoretical framework. Of course, you will tell me this is computationally quite expensive, but it works very well in one dimension. I should emphasize that unlike maximum likelihood and stochastic gradient descent in continuous time, what I'm presenting here works in one dimension. And for the scalar linear diffusion, linear in the sense of McKean, so where the drift and the diffusion do not depend on the law of the process, there's a very nice work by Kessler and Sorensen from the late 90s. And this can be done in a fully non-parametric framework, which is actually what I'm primarily interested in at the moment. There's a very nice paper by Kobet, Hoffman, and Marcus Rice from 2004, where they do this. Okay, now we can, in principle, use this approach, but of course, there is a difficulty in implementing this for the mean field dynamics, namely that the generator of the mean field dynamics is, of course, a nonlinear and non-local operator, right? So it's nonlinear since here it depends on the law of the process. And of course, it's time dependent, due to the law of the process. So what we do then is the following. We linearize the generator of the process of the mean field dynamics around the unique stationary state. Again, in terms of the theory, this works when we have a unique station. And now the point is that the following statements are equivalent: uniform propagation of chaos, uniqueness of stationary states for the mean field dynamics, exponentially fast convergence to equilibrium for the mean field dynamics. What we do then is we compare between this operator and this, in whatever operator theoretic sense you want. And this stability estimate, or whatever global asymptotic stability result that we have, that tells us that the solution to the McKean-Vlasov PDE converges exponentially fast to the stationary state in, say, relative entropy, means that we can show that, again, in some operator theoretic sense, these two operators are close. There is a very nice stability estimate for solutions to McKean-Vlasov PDEs by Rockner and Bogatsev. Some of you know that I'm kind of obsessed with. And there's some later work by Lacker. Now, the way we do it in the paper with Andrei is a bit different. But again, it's a nice PDE, right? So basically, it's telling us that if I look at solutions to the McKean-Vlasov PDE and I look at solutions to the linearized PDE around, when I linearize around the unique stationary state, then the solutions are close. So let's see how we can use this. So I observe a single particle, and again, I insist on this. So I think in this paper, there are two kind of, to my mind, interesting observations. First, this kind of abstract linearization step. And second, the fact that we can observe a single particle. And I don't want to observe more. The point being that since I have uniform propagation of chaos, if n is sufficiently large, the particles become uncorrelated. Right? So the amount of information that is contained in a single trajectory, discrete equidistant, so the low frequency limit, discrete equidistant observations of a single particle should be sufficient so that I can learn the parameters in the mean field model. And we can indeed do this. So so we solve then the eigenvalue problem. We compute, again, so there are lots of technical questions, how many eigenvalues and eigenfunctions we need to compute. It turns out we need to compute very few. But so that we carry out this program, we do this for the linearized operator, and from this we read off the parameters in the mean field dynamics. And so you can write it as a kind of pseudocode. So the input is discrete observations of a single particle. And then we learn the invariant measure. Now, for this particular case, the way it's written here is for this particular case, this particular choice of confining and interaction potentials, for which we can parameterize the invariant measure. So the invariant measure is of the form, well, 1 over z, e2 minus beta v of x plus kappa times x part over 2 minus m times x, m being the first moment, the magnetization. So we learn the magnetization from data, and then we proceed with so with computing the score function and then setting it equal to 0. And what we prove, so I don't state it as a theorem here, but so this is what the main theoretical result of this paper is, that if I send both m and n to infinity. Now note, I'm interested in, what I exploit here is the fact that the solution to my Marquin-Vlasov PD converges to rho infinity exponentially fast. So I will observe a single particle, a single trajectory, but I need the number of observations to go to infinity, because this means since I have equidistant observations, that I'm sort of reaching the stationary regimes. The regime described by the invariant measure. I need to make an assumption on the number of observations relative to the number of particles. Again, I repeat, not the number of particles that I observe. I'm still observing a single particle, but the way I pass to the mean field limit. Okay, so if m is of little o of n, then I have that my estimator is indeed unbiased, and I get the right rate of convergence, 1 over square root with respect to time and 1 over square root with respect to the number of particles. And if I make a slightly different assumption on the scaling between the number of observations and the number of particles, I also get a central limit theorem. And again, I repeat, the difficulty lies in proving that this is indeed invertible. Which sometimes so I can tell you more about this later. Okay, so if I apply this methodology to my good friend, the quadratic, sort of Landau potential and quadratic interaction, then as long as I have a sufficient number of observations, I can estimate the parameters correctly. And the number of particles can be quite low. So you can see even with n equals 25, I can do something reasonable. With n equals 250, I'm certainly estimating the parameters correctly. And the point is that for this type of mean field limits, you certainly don't need to reach the Avogadro number, right? So what is it? 6.023 times 10 to 23, whatever, right? You don't need 10 to 23 particles in order to reach the mean field limit here. Okay, this is not the type of kind of whatever mean field limit that one is interested in kinetic theory. Okay, now I mentioned that so for the theoretical results, we need to assume uniqueness of stationary states. But in principle, if you know the branch on the bifurcation diagram on which you are, so here for this model, we have a second order phase transition. It looks like this. And this is the value of the magnetization. So m is equal to 0 here, then this becomes unstable, and m is whatever it is here. So what we do then is we first estimate the first moment from data, and then we know on which branch of the bifurcation diagram we are, and then we perform the linearization around the correct invariant measure. This works very well. I mean, it should also be possible to prove that if you're in the right basin of attraction, you can do this, but we don't have yet. So we can do this below or above the phase transition. Again, as I mentioned, so one interesting question is whether you can learn phase transitions from data. And this is a quite simple example because you have an order parameter, which you know a priori. A more interesting question is learning order parameters from data. And this is what is done in this paper with Yanis Kevrikidis and George Kevrikidis as well. Okay, so then you can also break sort of symmetry and so on. Let me maybe, so how much time do I have? I guess 5 minutes, a bit more. I'll start a bit. Okay. So you can also use this so-called method of moments. So if the drift and the diffusion coefficients in your SD are polynomials, for example, then the standard old-fashioned method of moments actually works extremely well for this problem. And Andrea and I couldn't find it in the literature, so we thought, and it's a bit surprising that it hadn't already been done for the mean-field dynamics. But anyway, so this was published in SciMGQ earlier this year. Well, after we finished this, so there was also a paper by the group in Paris, so it's on Catalotte and Laredo, where they did more or less same thing. And now there's an extension of this where they try to turn this into a non-parametric method. But then they have to assume that they're observing particles from the mean field dynamics, which, as I mentioned, I don't like this. I think it doesn't make much sense to observe mean field particles. Okay, so here's then our interacting particle system. Again, I'm in 1D. It's very easy to extend this method of moments estimator to multidimensional problems. So here's essentially for notational simplicity. Plus, it's very easy to add non-degenerate noise. So as long as this function hates there, it's bounded away from 0, and it's polynomial, we're fine. So yeah, so we assume this structure so that the confining interaction terms as well as the diffusion coefficient are polynomial. And then we use Ito's formula, or we multiply the McKim-Lassov PD by equation by monomials and integrate and blah, blah, blah. So we obtain a system of equations for the moments that, for the coefficients, sorry, that involve the empirical moments. Okay, very simple stuff. So you can, yeah, so we can do this. And naturally, this resulting system is easy to solve. Again, assuming that it has a solution, I repeat, there are issues with non-identifiability in this business of mean field SDs and of inference for McKin SDs. But assuming that, I mean, either proving that the matrix is invertible or imposing additional assumptions, we get convergence with the right rates. Okay, 1 over square root of t, 1 over square root of n. And again, I insist we only need to observe a single particle. Okay. And even though what we prove applies to the uniformly elliptic case, you can also do hyperelliptic problems. So this is this Fitzko-Nagumo mean field SD from the neurosciences, which actually it also exhibits phase transition. So this again, we're below the transition point, and using our method of moments, we can learn the parameters in the mean field model. In the remaining 1 or 2 minutes, I will just advertise. Well, I will tell you 2 things. First, so as I mentioned, so this can be done quite easily in a non-parametric setting. So you can assume, for example, that you have an interaction potential that is sufficiently smooth so that it admits a nice kind of Fourier series representation. And then you want to learn the Fourier coefficients of your model. And as long as you have sufficient regularity, again, this works very well. So this is the example where we take the wrapped Gaussian. So Gaussian in quotation marks because we're on the torus. So we take the wrapped Gaussian. You, of course, have a nice Fourier series representation for the wrapped Gaussian. And we learn the Fourier coefficients of the wrapped Gaussian using stochastic gradient descent in continuous time. So this is what I refer to as semi-parametric. Okay, because again, I'm assuming that I can represent the function that I want to learn from data via a truncated Fourier series, and then I can control the error. So the last thing that I would say, and I won't get into details, is that we can also do Bayesian non-parametric inversion or inference from a KNSD. So this is done work with Richard Nicol from Cambridge and Colin Rai from Imperial. So if I now change completely my measurement model, and I assume that I'm observing actually solutions to my McKim-Lassov PDE, noisy. I have noisy observations to the McKim-Lassov PDE. I want to do a Bayesian non-parametric inference. And well, I will present it here, but I won't be able to, don't have time to explain what we do. But anyway, so if you have the standard Gaussian prior, And then if you assume appropriate regularity on both the interaction potential and the initial condition, then you can indeed recover the interaction potential. So here I'm in the case where I don't have a confining potential. I only have an interaction potential, and I'm on the torus. Okay, so I can prove posterior. Well, we have been able to prove posterior consistency, and the rate that we get is optimal in the sense that you have this delta n that depends on alpha being the Sobolev regularity of the interaction potential, beta being the Sobolev regularity of the initial condition, b being the number of dimensions. And if you send alpha and beta to infinity, so in the parametric case, if you like, you go back to 1 over square root of n. So again, I state a result here without really telling you very much, of course, but you need to make some assumptions on the initial conditions so that you can deconvolve. So the main issue is how you do the deconvolution. And for the kind of data that you need is local. So you have to stay relatively close to the origin, t equals 0. So we don't need any long time behavior here, which means that we don't have to worry about non-uniqueness of stationary states. Okay. And I'm happy to tell you more about this. Yeah, so maybe I should just, without having actually told you, well, this is the sort of result that we prove, so W being the true interaction potential, but without really having told you very much about what it is that we actually prove, I'll tell you what it is that how we prove it. So there is this very nice work that Richard has done on Bayesian nonlinear regression. Fantastic. He develops a very nice theoretical framework for doing Bayesian inference for PDEs. Then we use the same kind of stability estimates that I mentioned earlier. So in all this business, all the problems that I have worked on inference from McKinney's, the crucial step is a linearization step. At some point, you need to linearize the dynamics, and you can do it in lots of different ways. And then there's some very nice stability estimate by this paper by Bogatsev, Faulkner, and Sapoznikov that we use in Spirit. I mean, well, anyway, so I won't get into this. But anyway, so there's some very nice PDE theory involved, and then you also do parabolic regularity theory. Okay, so let me maybe finish by commenting that this is a very nice area, right? So inference for mean-field models is very nice because it's still new. Essentially, most of the papers that have appeared in this area appeared in the last 5 years or so. So there are still lots of nice things to be done. Okay, I'll stop here. Thank you.